Welcome to Friday Work. This is ChemActivity 2C. We're going to explore compounds, formulas, and molar mass. Let's focus on the learning outcomes. We're going to learn how to use molecular formulas to count both molecules and atoms. We're going to know how to determine the molar mass of a compound and what that is, and use conversion factors to convert between AMU, grams, moles, molecules, and atoms. So far in the course, we've focused on the structure of atoms and the mass of atoms, including the weighted average mass of a sample. Now we're going to take a step up and recognize that atoms can be combined into compounds, into molecules that form compounds. So let's first look at all the different ways we can represent a molecule. In this case, we're going to be looking at methane, and we can represent it in a couple of different ways. This first one is called a molecular formula. It just has the letters and some numbers. The second one is a structural formula. It shows how the atoms are connected to one another, but it's flat, it's two-dimensional. The third is what's called a ball and stick model. So you can see it represents a carbon and then 4 hydrogens, and it represents a kind of three-dimensional space. And then the last is called a space-filling model. So this is probably closer to the shape of an actual methane molecule, where you've got a carbon and it overlaps in space with the hydrogen atoms. One of the things we'll learn later in the semester is how does this actually occur? Let's ask some questions. How many hydrogen atoms are in a molecule of methane? Well, let's look at all the different representations and see what we can recognize. We see a 4 here, but if we didn't really know what that meant, we might not recognize how to interpret that. It's a little easier to see here in the structural formula or the ball and stick or the space filling, because we can count 1, 2, 3, 4 hydrogens, and that tells us that this the subscript here must refer to the number of hydrogens in the molecule. So 4 hydrogen atoms. Are the 4 hydrogen atoms bonded to each other in the molecule? What does the 4 mean in the chemical formula? So if we were just looking at the chemical formula, we actually can't tell how they're connected to one another. But we can see here that the hydrogens are not bound to each other, they're connected somehow to the carbons. So the answer to the first question is, are the 4 hydrogen atoms bonded to each other? That would be a no. So the 4 only means how many there are, not how they're connected. So let's look at a couple of other examples. We're given a ball and stick model here, and I actually gave you the formula, but I want to know, if you're given the ball and stick model, can you write a molecular formula from that? So how would we do that? First of all, we would recognize that there's 1 boron, and the other element that's present is fluorine, and we can see that there are 3 different fluorines, so we give that a subscript 3. So in a chemical formula, to write a chemical formula, we just write down all the elements, and then we write down how many of each. We do not need to write down a 1 next to the boron, because if there's no subscript, we understand it to be a 1. Let's look at another example. How many hydrogen atoms are in a molecule with this formula? So C2H5OH. So in this particular case, we can see, well, there's 5 hydrogens here, but then there appears to be another one here. And we'll learn later about kind of why we might write it that way, but here we can see that there would be a total of 6. All we need to be able to do right now is count. The other thing we can see in this formula is there's 2 carbons and 1 oxygen. So we learned in activity 2B how to count atoms in terms of moles. We're also going to need to do that with molecules and compounds. So let's start here with model 2. We can see we've got a unicorn and a methane molecule. How many horns would a dozen unicorns have? Well, if we could line up a dozen unicorns and each one has 1 horn, we would then say there would be 12 horns if we had a dozen unicorns. How many legs would a dozen unicorns have? Well, if we had a dozen of them, they each have 4 legs, so we would have 48 legs. How many legs would 2 dozen unicorns have? Well, 2 dozen would be twice that, so we would have 96 legs. Now let's apply this to a compound, because remember, part of the reason that I introduced this with dozens is because we generally are pretty comfortable thinking in terms of dozens and doing this kind of counting without realizing that we're essentially doing conversions. So let's look at some molecules. How many carbon atoms are there in a dozen methane molecules? Well, if we were to write out a dozen of these, 12 of them, we would have one carbon atom in each one. So we would have 12 carbon atoms. How many hydrogen atoms? Well, if we were, again, to write out 12 of these, and there are 4 in each one, so we would end up with 48 hydrogen atoms. Now, let's go to moles. So the same kind of thinking that we've just been doing with dozens, let's think about it in terms of moles. Remember, I'm just going to write it up here, that a mole is a way of counting a large number of things. And anytime we have a mole of something, we have 6.022 times 10 to the 23rd of those things. Just like anytime we have a dozen, we have 12 of those things. So how many horns would 1 mole of unicorns have? Well, if we could write out 6.02 times 10 to the 23rd unicorns, each one has 1 horn. So we would have 6.022 times 10 to the 23rd horns. How many legs would 1 mole of unicorns have? So each one will have 4. I'm going to start writing out how this would work mathematically, so you can just see it with these bigger numbers. So I've just set it up here. We have a mole of unicorns, which I've already just translated that into 6.022 times 10 to the 23rd unicorns. And I know that I have 4 legs in each unicorn. And so what that gives me is 2.409 times 10 to the 24 legs. So a lot of legs if we had a whole mole of unicorns. How many legs would 2 moles of unicorns have? Well, we would just double this, because if this is 1 mole of unicorns, if we had 2 moles of unicorns, we're going to have twice as many legs. So that number comes out to be 4.818 times 10 to the 24th legs. So just like we were counting with atoms, we can count multiple things, particularly things that are more complex, like a unicorn or a molecule. Let's now start to apply this to molecules. The first step here asks us to complete the conversion factors below. So let's give ourselves some space here. So based on knowing what a methane molecule looks like, we can write a conversion factor that tells us how many carbon atoms there are in 1 molecule. Well, I can see in 1 molecule, I'm going to have 1 carbon atom. I'm going to have 4 hydrogen atoms. Now, that's true if I'm just counting an individual molecule. That means I've got an individual atom or 4 individual atoms. But what if I had a whole mole of methane? Well, if I had a whole mole of methane, that would be 6.02 times 10 to the 23rd of the molecules. That also means I would have 6.02 times 10 to the 23rd carbon atoms. And so that would mean I would have 1 mole of carbon atom. And likewise, I would have 4 moles of hydrogen atoms if I had a whole mole of methane molecules. So we're going to practice using these conversion factors by looking at the problems on the next page. So the first question says, how many carbon atoms are in 243 methane molecules? So the first thing I want to notice is, what are we converting from and to? So we're starting with atoms and we want molecules. That means we're going to be looking for a conversion factor that relates atoms and molecules. Let's see if we can write one down. I know that in 1 CH4 molecule, I have one carbon atom. So that's one of the conversion factors we wrote on the previous page. Now, how would we use that conversion factor? As in other conversion problems, we're always going to start with what we're given. 243 CH4 molecules. Notice that I'm writing out the whole darn units. I know it's a lot of writing, but I need to be able to see what it is I'm starting with and what its units are so that I can cancel things out. Now I want to go from molecules to atoms, so I'm going to look for a conversion factor that has molecules in the denominator so I can cancel it out, and atoms in the numerator. And look, I've got it all written out here already in the right format. So you can see my CH4 molecules will cancel, and I'm going to be left with carbon atoms. And so because there's one carbon atom per molecule, the numerical value of my calculation doesn't change, 248 carbon atoms. And so let's think about what we've done in this conversion. We had a sample, 243 methane molecules. We're not changing the sample at all. We're just asking to describe the sample in a different way. And what we're saying is, instead of describing it based on the number of molecules that are there, now we want to describe it based on the number of carbon atoms that are there. And this calculation allows us to do that. If our sample has 444 hydrogen atoms, how many methane molecules do we have? So as with other conversions, we're going to start with what we're given, 444 hydrogen atoms. Now we want something that's going to take us from hydrogen atoms to CH4 molecules. And if you go back to the previous page, you have a conversion factor that relates those two units. So we want something that has hydrogen atoms in the denominator and CH4 molecules in the numerator. And if we go back and look, we know that there are 4 hydrogen atoms for every one molecule. And so what we're going to do now is we can see that the hydrogen atoms will cancel. And what we're left with once we do the math is 111 CH4 molecules. So again, we're starting with a sample that was described in a particular way. It was a sample that had 444 hydrogen atoms in it. We're not changing the sample. It's still sitting on the counter there, or in a jar, or wherever you want to envision it's going to be. And all we're doing is saying, let's describe it not based on the number of hydrogen atoms, but based on the number of molecules that are present. And this conversion factor allows us to make that relationship. Now let's start working with moles. How many moles of hydrogen are in 3.2 moles of CH4? Again, start with what we've got, 3.2 moles of CH4. And we're going to look for a relationship between moles of CH4 and moles of hydrogen. And we created that on the previous page. So for every 1 mole of CH4, we know there are 4 moles of hydrogen. So what we get when we plug this into our calculator is we get 12.8 moles of hydrogen. But let's stop and look at the sig figs here. One thing to first notice is that these relationships, which came from the chemical formula, are exact. So they're not going to limit our significant digits. They don't have any uncertainty in them. In other words, we know for sure that in a mole of CH4, there's exactly 4 moles of hydrogen. This, however, is a number that does have uncertainty in it. So we're going to be limited to 2 sig figs in our answer. So that means that the 8 is not going to be significant. We don't have any idea what the value of the 8 is. So we are going to round to 2 sig figs to say 13 moles of hydrogen. Let's do a couple more. If we have a sample of methane containing 7,516 moles of hydrogen, let's start with that. 7,516 moles of hydrogen. The question is, how many moles of methane do we have? We'll go back to the previous page, find a conversion factor that relates moles of hydrogen to moles of methane. We know that there are 4 moles of hydrogen for every 1 mole of CH4. Let me just pause here and say this is the same conversion factor we used here, but notice it's flip-flopped because here we were starting with moles of methane and here we're starting with moles of hydrogen. So what we get when we do this calculation, first of all, the moles of hydrogen cancel out. And what we get is 1879 moles of CH4. So we had a sample. This is how many moles of hydrogen was in it. But if instead of counting by hydrogens, we wanted to count by CH4, this is how many moles of CH4 there would be. Now, the question is how many moles of carbon are there? So we probably don't want to start from here because this doesn't have carbon in it, but we could start from here. So we could now say, all right, let's do a second step. If we start with 1879 moles of CH4, we know that for every mole of CH4, there is 1 mole of carbon. So that's one of the conversion factors we created on the previous page. And so that means we're going to have 1879 moles of carbon. Remember, these will cancel. So even though the number is the same here, they mean different things. It just happens that if we count up the moles of CH4 or we count up the moles of carbon, it happens to be the same number because, of course, it's a one-to-one relationship. I am not going to take the time in this video to complete the application questions. The solutions for these other problems are posted online in the solutions folder. And if you have questions about how to set it up or how to solve it, absolutely come and see me or come into the CIC. I'm going to continue on to the next page. Okay, so far what we've been doing when we've been using moles is we've been counting, right? So just like when you use dozens, you're counting things. Now we want to take that counting and connect it to the weighing of things. So we learned in ChemActivity 2B that we could calculate the average mass based on all the isotopes that would be present. And for a carbon atom, the average mass is 12.01 AMUs. That's the average of carbon 12 and carbon 13 and a very little bit of carbon 14. Those 3 isotopes mostly make up the samples of carbon. But this is the average mass. It happens that a mole of carbon atoms also has a mass. So if we got 6.02 times 10 to the 23rd carbon atoms and laid them out on the table and put them on a balance, they would have a mass of 12.01 grams. Now you might say, well, isn't that coincidental? And it's not coincidental. That's partly how we define what a mole is. We define a mole so that this relationship will be the same number, right? Numerically, this is 12.01. Numerically, this is 12.01. But this is a very, very small amount of mass, and this is a larger amount of mass. Just for your benefit, a nickel weighs about 5 grams. So this would be about 2 nickels worth of carbon atoms. And this would be something you wouldn't ever be able to even detect with a normal balance. So here's some things that we can look at. If we want to convert between counting atoms and counting moles, this is something we've been doing. We've been using this relationship. If we want to go from counting atoms to the mass of an average atom, we can do that using the average atomic mass. If we want to go from counting moles to the mass of a sample in grams, we can use this, what's called the molar mass. So let's just review those definitions. The molar mass is the mass of 1 mole of something. The atomic mass is just the average mass of an atom. And remember, no atom actually has that mass. This is the weighted average. So let's look at this scheme a little bit. Study the conversion scheme in Model 3. Find the places in the scheme that show the two conversion relationships for carbon. So let's see where those are. One is here. 1 carbon atom equals 12.01 AMUs. And one is here. 1 mole of carbon is 12.01 grams. Why do we have two relationships? Because we have, in one case, we're just counting a single atom, and in the other case, we're counting a whole mole. One thing to point out is that we do have a conversion here, but this is not specific to carbon. So we can use this, remember this relationship, a mole of atoms is 6.02 times 20 to the third atoms or donuts or whatever we want. This doesn't matter what kind of atom it is. These, it does. Now, if we look at the periodic table entry for sulfur, we're going to find 32.06. And on the periodic table, it doesn't give us any units. But what we've learned is that that number means two different things. It means 32.06 AMU, which is the atomic mass. And remember, this is going to be an average mass. It's an average of sulfur 32 and sulfur 34 and 35. I can't remember all the isotopes, but it's an average. But this is the average mass of a single atom. The other thing is it's 32.06 grams for a mole of sulfur. So this is the molar mass. I want to go one step further and write these out as full conversions. So one way we could write this is 32.06 AMU per atom, per 1 atom of sulfur. Or we can say 32.06 grams for 1 mole of sulfur. So now we've got two conversion factors we can use. And remember, we can flip them around depending on where we need the units to be. But these are two relationships that are going to be really handy. How would we use them? Well, what if we knew atoms and we wanted to get the mass in AMU? Or if we knew AMU and wanted to get the number of atoms? Or if we knew a mass in grams and wanted to know how many moles of sulfur? Or if we started with moles of sulfur, we could go to grams. All right, so this table in question 16 is just going to get us to think a little bit about how do we use these ideas without actually doing the calculation yet. So let's look at the first one, which is already done for us, but I think it will help us to talk through it. If we had a question and we said, how many atoms are in 3.2 moles of nickel? This is a conversion between two ways of counting, because counting atoms and counting moles is still counting how many things are there. And the conversion factor we would use is to go from moles to atoms. And this is not written like a fraction, but it's written as the equality that we could turn into a conversion factor. So the second question, what is the mass of 0.453 moles of nitrogen? So 0.543 moles is a way of counting how many nitrogens do we have. The question is asking for mass. So this is a conversion between mass and counting. Now, this is the harder question. What conversion factor would we use? So we need something, and I'm just going to write in the margin here, we need something that's going to convert grams to moles. That those two things are going to be involved in the conversion factor. And remember, because we just did it on the previous page, that because we did it for sulfur, if we go to the periodic table, what we'll find is that there's a number there, 14.01, and that's either the molar mass or the atomic mass. In this case, because we're dealing with moles, we want the molar mass, so we're going to say 14.01 grams equals 1 mole. And so we could use that to create a conversion factor that we would use in that case. Let's look at the next one. How many atoms are in 3.03 AMUs of hydrogen? So 3.03 is a mass. It's something we would weigh on a balance, and we want to know how many atoms. So this is going from a mass to counting. And in this case, we're dealing with hydrogen, and we are, and we're dealing with AMUs, so we're going to want the atomic mass. So we go to the periodic table, we find that that says 1.008, and that's going to be AMU equals 1 atom. I'm just going to do this so that it's clear that that's just kind of an annotation. So notice that in these two cases where so far, where we were converting between mass and counting, we needed to go to the periodic table to get the numerical value that we needed, and then we needed to make sure we attached the right units to it. So let's look at another one. We've got a sample of chlorine that have a mass of 7.2 grams, and we want the mass in AMU. So this is actually going from mass to mass. Now I want you to go back to the previous page, look at the scheme in Model 3, and look at the bottom of it. We didn't really focus on it when we were looking at the scheme earlier, but there's a conversion factor there that relates AMUs to grams. And here it is. Remember, 1 AMU is a little bitty bit of a gram. But if we were converting from grams to AMUs, we could use this conversion factor. Notice that, like the case up here, this is independent of what kind of atom we have. This is independent of what kind of atom we have. This is just two different ways of measuring mass. It's like going from grams to pounds, only in this case it's going from AMUs to grams. In the case where we went from mass to counting, we needed to know what kind of atom we had because we needed to find this number in the periodic table. All right, let's do the last one. A sample of neon has a mass of 2.15 grams. How many moles are in the sample? So this is going from a mass to a way of counting. And as in the previous cases, that will clue us in that we're going to need to go find some information about the mass and the relationship to counting from the periodic table. So in this case, we're going to moles, from mass to moles. So we're going to want the molar mass. And so if we go to the periodic table for neon, what we find is that 20.18 grams is equal to 1 mole. And just to remind you, the only thing you're going to find on the periodic table is the 20.18. We just need to know that what we are allowed to say that is a mass in grams if we're counting 1 mole of neon. Now this next question is a really important one conceptually. Which of the above examples are counting by weighing? Let's first talk about what counting by weighing is. So in the laboratory, we can't take a sample out and count out like, okay, here's 80 atoms of carbon. We just can't do it, they're too small. So but what we can do is weigh out a certain mass of carbon, and if we know something about carbon, we can convert that mass into a number of carbon atoms. So let's look at how that worked in this case. So if we started with a mass here and ended up with moles, that would be counting by weighing. So we can see that B is an example of counting by weighing because we weigh it and then we're able to count it. It's also the case that sample E is we start with a mass and then we figure out how many moles, so that's a counting by weighing. Sorry, B. The others are conversions, but they're not examples of counting by weighing. So, question 17. Some problems require us to use more than one part of the scheme in Model 3. So, for example, if you had a sample that had 0.457 grams of silver, and I want to know how many atoms are in the sample. What we've seen is that we have examples of where we can go grams to moles, but this question is asking grams to atoms. So let's think about how we would start. We would start with grams, and then we could go to moles, and we would do that by using a molar mass. And then we could go to atoms by using the definition of a mole, because we know that 1 mole equals 6.022 times 10 to the 23rd. So we would essentially be using, I'm just going to flip back to my page for a minute. So if you go back to the scheme in Model 3, we would be starting on the bottom right and going up to the top left. So if you just see, we would be starting down here and then going there if you look back at the scheme in Model 3. As before, I'm going to leave the application questions for you to do on your own. The answers are posted, and feel free to come get help. These kinds of conversions are often tricky for people until you get your head wrapped around it. So if you feel a little overwhelmed, that is not at all unusual. Just keep asking and ask for more practice and ask for help. Okay, so we've defined the molar mass for an element, for atoms. We haven't done it for compounds. So by definition, really similar to the case for atoms, the molar mass of a compound is the mass of a sample that contains 1 mole of molecules. So let's think about how we would figure that out for something. So remember we were talking about methane earlier, CH4. And so we know that in a molecule, if we have 1 molecule, that means we have 1 carbon atom and 4 hydrogen atoms. We also know from the periodic table that 1 carbon atom is 12 AMU, and each hydrogen is 1.008. So I'm going to say 4 atoms times 1.008 AMU per atom, and that's going to give me 4.032 AMU. Let's just stop and ask what we just did there. My 1 carbon atom contributes 12.01 AMU to the mass of a CH4. The 4 hydrogen atoms contribute 4.032 AMU. And if we add that up, we're going to get the total mass, and that's going to be 16.04 AMU. And notice that I truncated my sum after the 100th place, because I only knew the 100th place here. So even though I know the 1000th place here, I'm not going to include that in my final sum. So what this tells us is a single molecule of CH4. So a carbon with 4 hydrogens, its mass for a single molecule is 16.04 AMU. This is the molecular mass of methane, the mass of a single molecule. But now let's think about if we had a whole mole. So we know that if we had a whole mole, we would have 1 mole of carbon atoms, and we would have 4 moles of hydrogen atoms. Now we also know that a mole of carbons, remember we've been looking this up on the periodic table, is 12.01 grams. That's 1 mole. For the hydrogens, we have 4 moles, and we have 1.008 grams per mole. So we have 4.032 grams. And if we add that up, we get 16.04 grams. This is equals to 1 mole of CH4. So instead of having, in this case, we had 1 molecule, that's its mass. If we had a whole mole of these, if we lined up 6.02 times 10 to the 23rd of them and weighed them, their mass would be 16.04 grams. And that is by definition the molar mass. Remember, the molar mass of a compound is the mass of a sample containing 1 mole of molecules. So if we wanted to calculate the molar mass of some other compound, like this is magnesium chloride or this is glucose, you don't need to know those names yet, but if we wanted to calculate their molar mass, what would we do? Well, we would add up the masses of all the individual atoms. And in particular, we're going to take the masses of all the elements, but we're going to count them in moles, because remember that we want the molar mass here. And the other thing we're going to make sure we do is account for how many of each there are, right? So if there were 2 chlorines, we're going to have to take that into account, just like we had 4 hydrogens here. So we need to take account of the numbers that are in the formula. And ultimately, really what we're doing is we're adding things up. We'll do one example of that in just a minute. But before we do, let's write the molar mass of CH4 in terms of a conversion factor. So we saw on the previous page that 16.04 grams equals 1 mole of methane. And we can convert that into a conversion factor by saying 16.04 grams is 1 mole. So we can use this as a conversion factor. If we've got grams, we can go to moles. If we've got moles, we can go to grams. So let's see how we use it. I didn't leave very much space here, but you'll see it. How might we use this conversion factor to answer the following question? What is the mass of 2.5 moles of CH4? So just like in other conversions, we're going to start with what we're given, 2.5 moles of CH4. So what that means is we have 2.5 moles worth, kind of like 2.5 dozens worth of CH4, only it's a lot bigger than a dozen. And we want to know what is the mass. So we need something that relates moles, which is what we have, to mass. Unfortunately, we have something. And so we're going to set this up. We're going to make sure that moles of CH4 are on the bottom and grams are on the top. And that we can see that we've got to put the 16.04 with the grams and the 1 with the moles, because that's, when we calculated, that's what we came up with. It came from this, so the 16.04 needs to stay with the grams. And so what we get numerically is 40.1 grams. The moles cancel. We should be limited to 2 sig figs because this only has 2 sig figs. So we're going to round that to 40.0. 40 point. And that will help us to show that both of those are significant. So does that make sense? So if a single mole has a mass of 16.04 and we've got a little more than 2, we've got 2.5, 40 grams is a number that makes sense. I'm going to go ahead and do this first application question because I just want to make sure that you know how to calculate the molar mass of something. This one is a little bit complex. We haven't even seen all the things associated with this yet, but that's good because you're learning it now. So we've got this formula, magnesium 3, PO4 in parentheses times 2. So the parentheses means that everything that's inside the parentheses gets doubled. So if we were to count up all the things, we've got 3 magnesiums, plus we've got 2 phosphoruses, plus we've got 8 oxygens. So let me just make sure that everybody's clear how I got the 2 and the 8. This 2 outside the parentheses is going to double everything. So even though there's 1 phosphorus inside, we're going to double it. And there's 4 oxygens inside, so we're going to double it. So we get 3 magnesiums, 2 phosphorus, 8 oxygen. And so if we look up the molar masses of those elements, what we're going to get is 3 moles of magnesium. And from the periodic table, we get 24.30 grams per mole for magnesium. So the moles are going to cancel. That's going to be grams of magnesium, plus 2 moles of phosphorus. And phosphorus on the periodic table is 30.97 grams per mole. And again, the moles will cancel. Plus, I'm just going to write down here because I've got space. 8 moles of oxygen, and there are 16.0 grams per mole for oxygen. And again, the units will cancel. And so what we do, I'm not going to write it all out, but 3 times 24.30 plus 2 times 30.97 plus 8 times 16. And my calculations get me, when I add all that up, 262.84 grams. And it turns out, and in the solution manual or the solutions that are posted online, you'll be able to see this. The tenths place is known, but the hundredths place is not known. So this would end up rounding to 262.8 grams. And that's for 1 mole of what's called magnesium. Oh, let's make that prettier. Phosphate. So that's its molar mass. Okay, the rest of the application questions are ones that you should work on your own and check your answers with the solution. I do encourage you to do the reflection questions. What have you learned? What questions do you have? Or what do you feel like you need more practice with? When you've identified what you need more practice with, then it's really easy to go into the Chemistry Instructional Center and say, I need help with converting mass to moles. Or I need to know, when do I use 6.02 times 10 to the 23rd and when do I take a number from the periodic table, or whatever the question is. If you do this reflection, it will help you to know what kinds of things to ask about. All right, happy Friday work.